Video will review the long division process on polynomials. But before we get into that, let's go back to a skill from grade school. If I had the improper fraction 271 over 4, to take this and match this up with the vocabulary, this you could think of as your dividend is 271 and the divisor is 4. To turn this into a long division problem, an easy way to memorize it is the O in divisor goes on the outside, and the EN of dividend, I always associate that with going inside. So just a little memorization trick right there. But I will run through the long division algorithm on a simple problem from grade school, and then I'll model it on a problem using polynomials. So I've taken 271 divided by 4, the improper fraction, and I'm writing this now as a traditional long division problem. So I've got my divisor of 4 and my dividend of 271. So the way you would run through the algorithm, how many times will 4 divide into 2? It won't, so you move over 1. How many times will 4 divide into 27? Well, it goes in 6 times. 6 times 4 is 24, and then I subtract that, leaving me with 3, and then the 1 drops down. How many times will 4 divide into 31? Well, that maximum number would be 7. So 7 times 4 is 28. 31, subtract 28, leaves you with 3. So 3 is what's called our remainder. So to match this up with the vocabulary, my quotient would be 67, my remainder is 3, and my divisor is 4. Or you probably would have presented the answer in 5th grade like this, 67 and 3/4. But really, this is what you were doing. So let's take this thought process and apply this to polynomials. And what this skill will help you do, it helps you factor polynomials of higher degree, or find factors of polynomials whenever they have a remainder that's not 0. And you'll use this skill for graphing functions of higher order, higher degree, in Algebra 2 pre-calculus classes. So here's a problem from the textbook, number 14, that's presented as a rational expression. And before I get started with this, let me just test something out here. 2 divided by -10 is -20. Are there any factors of -20 that would differ by 5? And there really aren't. So this is not factorable by means that we know. So the only way I can break this down is to use a long division tool. So I would recreate the rational expression as a traditional division problem. And setting this up for you already, so you would be expected to know to do that. I've got the divisor of 2x plus 1 and the dividend of 2x squared minus 5x minus 10. So the way this would work, you would compare the 2x with 2x squared. And an easy way to think about it is, what would I need to multiply 2x by in order to get 2x squared? So the missing factor would be an x. And the way I like to do these, I think it's best if you line these up in order of power. So I've got a squared term, a linear term, and a constant. So any piece of my quotient that would match that power, I would just line everything up. It just makes it easier. It just makes the problem flow nicer. So now to run through the algorithm, say x times 2x is 2x squared. Notice that I'm lining that up with the squared term. And then x times positive 1 is just simply positive x. So now I have this binomial expression, and the whole point of this step is to eliminate the x squared term. So I would take the opposite of the sum, or subtract these in a way so that the term 2x squared sums to 0. So 2x squared minus itself is 0, and then -5 minus 1x is -6. -6x. And then the -10 slips down, and the algorithm starts over again. So now I'm going to compare 2x to -6. What do I need to multiply 2x by in order to get -6? So the missing factor there is -3. So then you start the process. Negative 3 times positive 2x is negative 6x. The whole point or the whole goal in this particular step is to eliminate the term 6x. And then negative 3 times positive 1 is negative 3. So now I would add the opposite of that sum to the binomial above. Remember, the whole goal is to eliminate 6x. So 6x minus itself, or plus the opposite, would sum to 0. And then you would have negative 10 minus negative 3, leaving you with negative 7. So negative 7 is my remainder, which means that, as we anticipated before we started, 2x squared minus 5x minus 10 is not factorable by methods that we've learned in class. So the way you would present your final answer, you would have a quotient of x minus 3 plus the remainder over the divisor. Or you could present your answer as x minus 3 minus, since the remainder is negative. And you could just simply leave your final answer in either format that's given. Okay, let's look at number 20. And in number 20, I went ahead and just set this up as a long division problem. So I've got my divisor of n minus 1, and then my dividend of n cubed minus 1. And I've gone ahead and turned this into long division, and I'll use this example just to show you a method for handling this whenever you're missing powers along the way in a dividend. So I've got the cube, the square, the first, and the constant. So I'm putting holders in place with coefficients of 0 so that I account for each power in the trail. So let's start the process. Comparing n to n cubed, the missing factor is n squared. So I'm going to line that up in the n squared column. And then I start the algorithmic thinking. N squared times n is n cubed, keeping in mind that the whole point of this particular step is to eliminate the n cubed term. And then n squared times negative 1 is negative n squared. And remember, I'm adding the opposite here. So n cubed leaves the picture, and I now have 0 n squared minus negative n squared, making that a positive n squared. And then just to keep things organized and in place, I'm going to slip down 0n. And now I start the process over again. So now I'm going to compare n to the n squared that's sitting here. The missing factor is n to the first. So I will line this up in my quotient. So I now have positive n times n, giving me positive n squared, and then positive n times negative 1, giving me negative 1n. And I'm going to add the opposite. So n squared leaves the picture, and now 0n minus negative 1n, the end result there is just a positive 1n, and then negative 1 slips down. And then the process starts over again. So now in this particular step, I'm going to compare the n with the n that's sitting here. Well, their common factor or missing factor would just simply be positive 1. So I put that in my quotient. So 1 times n is n, and 1 times negative 1 is negative 1. And when I add the opposite, you can see that this sums to 0. Both terms disappear. So here, my remainder is 0. When the remainder is 0, that means that you could have factored the original dividend. This is a difference of cubes, and the first factor in the difference of cubes would be n minus 1. Remember our little pattern. The first binomial factor has the same operation as the original, and then each term in the first factor is the cube root of each term from the binomial difference. This is a difference of cubes, perfect difference of cubes, an old topic. And then our pattern tells us that the trinomial factor then would start squaring the first term. Everything in the trinomial factor is now positive because I've already accounted for the negative term. The second term is the product of the two. And then the last term is the square. So you can see that that's what I ended up with right here. But I went through the process. It's still a very good problem to show you how to line these up whenever you're missing powers along the way in your dividend. And I wanted to show you what happens when the remainder is 0. So maybe you caught this early on before I got started, but I just wanted you to see that the math holds, everything verifies with this. Let's do one more from the pizzazz. I would like to do number 5 on the pizzazz with you right now in the video. So here's number 5 in the pizzazz. So before I get started with this, let's just see if it's factorable. 3 times negative 11 is negative 33. Are there factors of 33 that differ by 5? And there aren't. 3 and 11 differ by 8. So the only way that I can take this apart is to use long division. So I'm going to set up my long division. X plus 1 is my divisor. And then on the inside, and now I start my algorithm. Comparing x to 3x squared, well, that would need a factor of 3x. So 3x times x is 3x squared. The whole goal in this step is to eliminate 3x squared. And then 3x times 1. And then I'm going to add the opposite. So 3x squared leaves the problem. And I have negative 5x minus positive 3x. So I now have negative 8x. And now negative 11 slips down. And the process starts over again. So I'm now going to compare the x to negative 8x. So the missing factor is minus 8. Negative 8 times positive x gives me negative 8x. And then negative 8 times positive 1. And I'm adding the opposite. The whole point in this particular step is to eliminate the term negative 8x. So I have negative 11 minus a negative 8, leaving me with negative 3. So my remainder is negative 3, and the way that I would present my final answer, my quotient is 3x minus 8. My remainder is negative 3, and the remainder is written over the divisor of x plus 1.